to another day of CS219, day 15. Hope you all are doing great today. So today we're going to be talking about RAID, continuing up on chapter 7. And then with the remainder of the time, we will do a brief overview of chapter 8. So let's go ahead and get started by talking about the reason how RAID came to be. So, last time we were talking about hard drives, and we're going to pick up from that. And, let's say we're really hyped about hard drives, so we're going to go and buy a couple of them, right? So I have here on the different browser monitor a couple of hard drive prices for a unidentified hard drive from an unidentified website. And it turns out that looking at these prices, I'm actually like, wow, I think prices gone up a little bit. But here are the prices that I'm looking at. So I see there's a 500 gigabyte hard drive, and then there's a 1 terabyte hard drive, a 2, a 4, and apparently there's a 6. And these are $55.99. I'm just going to do some round up because it's too many numbers to write. So this one is $56. This one is $73. This one is $120. It's $119 actually, but yeah. And then $177, and then this one is $228. Okay. And so, if say that your boss, you're creating a data center or something like that, and your boss says we approximate that we're going to need approximately something like 32 terabytes of space. That's approximately what we want to have. And he sends you out to buy space for that. So, you're looking at these prices and you're trying to see which is the cheapest one to get. And you typically notice that the prices on, sort of as an estimate, they sometimes the twice the size, they double the price. But you also see that as the size increases, it's not exactly a double, because it's a little bit cheaper to buy twice the space in one drive up to a certain limit per se. So, looking at this, we see that the smallest drive is half a terabyte. And we can see that going up to 1 terabyte, it's not twice exactly. I mean, 56 times 2, it's going to be $112, right? And you can see that that's actually more of almost around the range of the 2 terabyte. So if what you wanted to buy was 1 terabyte, then no questions asked, this is a lot cheaper to buy than 2 of these. And you have the benefit of it being one single drive. So if you have a motherboard that has like 6 SATA ports, you're only going to be using 1 SATA port for this. And so that's a good thing as well, because you want to save space, and also uses less power, because 2 drives are going to use twice the power. And then by power, I mean actual electricity and wattage. Okay, but again, in this case, you gotta buy 32 terabytes. So let's go ahead and see if this is cheaper. This obviously is a lot cheaper to buy this than this, because you can see that this times 2 is about $146, which is a little bit more than this. And so, okay, and then clearly this is a better choice. But let's go ahead and look at the 4 terabyte. We can also see that that's even cheaper, because while this was the cheapest so far, this times 2 is $240, but that's a lot smaller than that. So then we kind of go with that, and you can see that kind of follows along. Once you get to the 6 terabyte, though, I don't see anything bigger than that. And what ends up happening, and this is a little bit easier, I suppose, to see when you're looking at like an SD card for like a camera, which is flash memory. So let me go ahead and pull up prices of those. Is sometimes they, you see that at the current time there's a limit on the biggest drive a certain company sells, and it's usually going to be the cheapest one in some scenarios. But in other scenarios, sometimes you'll see that there is a bigger drive, but it's a lot more expensive to the point that it's twice as big. So like if there was a 12 terabyte SSD, which probably in reality what you would see something like an 8 terabyte, you would actually see that it is cheaper to buy perhaps a 6 terabyte in terms of cost per bit than it is to get the bigger size. And that tends to happen sometimes for like the latest and most newest drive because of technology. So here I'm looking at some SD cards, and I think that will kind of apply that one, not this one. This one also kind of limits you. I've seen this usually before. I should have pulled up one that I had an example of that. Let's go ahead and I think I know. I think what about like the Samsung SD cards? Those are actually sometimes fall into that category. Let's see. Yeah, this one actually works out. So okay, so in this scenario with the, and I guess this one I'll say this is a Samsung Evo Select SD card. You have a 32 gigabyte. This is flash memory, so it's going to be more expensive than a hard drive. It's solid state, you know, we talked about that. And it's non-volatile because you want your pictures to last after you take them and not for them to be deleted when you turn the camera off. And so, interestingly enough here, the price of this is actually quite cheap, actually. But still, this is cheaper because, I mean, this is $56 versus this. In fact, we could compute the cost per bit by dividing... basically, well, we want to multiply gigabytes into what it really is, which is billions. So 500 billion bytes, you know, and we have $56. So let's divide it by, not just 56, I would say divided by 56, 5600. So we get cost per cent, because otherwise it's still going to be a pretty big number. But if we did it by dollars, we would just take 500 billion. So I'm putting in here on the computer billion, million, billion. If we did it divided by 56, it's still a really big number per that. So we're going to do a percent by putting 2 more zeros in there. It's still a pretty big number. So maybe instead of bytes, because this is not even bits, this is bytes. We're going to do it by kilobytes. Let's just do it by megabytes, just because it's not such a huge, insane number. So really, in 500 gigabytes, there is 500,000 megabytes, okay? So if we take that number and we divide it by 5600, we get 89 cents. Or sorry, 89 megabytes per cent. Yeah, okay? And so if we do that with the SD card here, or here, let's do it actually with the 6 terabyte one. So for the 6 terabyte one, it would actually be basically you're taking 600 6 million megabytes. Yeah, and then you're dividing it by 228, which 22,000. So that basically tells you that, and then so what I did is I take 6 million divided by 22800, which is basically the equivalent of cents, right? Because if we have $228 to multiply them times cents, you multiply them times 100. So you basically just add 2 zeros. So this division is going to give me 263 megabytes per cent. Okay, so 1 penny gets you that much space. Obviously, this is a lot cheaper than this. But if we do this with the SD card, you know, 32 gigabytes is going to be 32,000 megabytes. And if we divide that by 749, which again, we're going to multiply times 100, so it's just 749 like that. Then that one we're going to get 3200 divided by 749. We're going to get 42 megabytes per cent. So that's a lot more expensive, right? Because we're basically getting half of the price. But then again, this is a lot faster memory, okay? So you can see that while this is cheap, it's still more expensive than the hard drive. So anyways, let's go ahead and put the rest of the prices here, because this will lower the price. So we can see that this is twice the space, but it's not twice the price. When you get to 128, the reason I'm putting the pennies is because it's smaller numbers, so we actually want to see that when you get to 128, it's slightly cheaper, but not that much, as you can see here. It's basically $1, pretty much $1 cheaper, yeah. And then when you get to 256, this one is $34.99. So here it's considerably cheaper. And then something interesting happens for the 512. This one is actually $87.99. So it actually turns out that this one's a little bit more expensive than that one. But here, let's do the math on that. So 256,000 divided by $34.99, we'll just do 349, so we do cost per cents. So in that case, we are gonna have 256,000 divided by 3,499. That gives me about 73 megabytes per cent. And then the other one, which is 512, is divided by 879 or 8,799. That one gives me 58 megabytes per cent. That's low. In fact, here, let's just do this 128 one so we can compare it with that. That one is 128 divided by basically 2,000,1999. That's 64%. So you can see that this one and this one are both cheaper. So the 128 SSD card and the 256 SSD card are both cheaper than the 512 when we're looking at the cost per bit. So if all you care about is the biggest amount of space in terms of how much you can, how much money, you know, if you have a budget of $100 and you're trying to buy as much space as possible, then it's going to be a lot cheaper for you to buy as many 256 cards as you can buy, which would be approximately, you know, well, if you can spare a little couple of pennies extra, then you could buy 3 of those, and you would end up with basically 3 256 SD cards, which would be 256 times 3, 768 gigabytes, right? If you're, you know, if you really are stuck with the $100 as a limit, then you could probably buy one of the 128s and then 2 of the 256, and that would still be cheaper than trying to go with the bigger card because it's more expensive. So this is something that actually happens with some of the storage solutions, where yes, the bigger it is, the cheaper the cost per bit, but there's a limit to that. And that's typically because they're making these drives that are not very popularly bought, and they're basically the edge of the technology. You know, we're trying to keep going up, you know, Moore's law and everything. We're trying to keep adding more space to this, and these are sort of the latest generation of the drives that can contain the most information. So don't be surprised about this being a thing. Sometimes the biggest drive is not going to be the cheapest one. It's, you know, they're the extremes. It's typically like if you were to look at some sort of graph, you can see that the price starts up here, and then it goes down, it goes down, it goes down, and then at some point it kind of comes back up a little bit. In fact, the reality of things is it's probably more of like that. In fact, it's even more steep. It would be something like this, you know? And the reason why is that consumer products are probably going to be around this area here, you know, and this probably goes even higher, because consumer products are going to be like, you know, the hard drives or the SD cards and things like that are going to be there. And this is basically when we're looking at that biggest hard drive that we saw. So the 8 terabyte hard drive is going to be right at the bottom of this hill here. And then also it's going to be the 256 SD card right there. And then in the SD card territory, you can see that it kind of goes back up here, which is, you know, this is where like the 128 was. Actually, well, the 128 would probably around here. Then the 256, and then the 64 is here. And then the 512 is around here, which is more expensive than the 128, so it's a little bit high. I guess this is not exactly the scale. It will be more like around there. And then this is where the 512 is. So you can see that the 64 is more expensive than the 512 when we're looking at the cost per bit. So this is on a cost per byte. Well, technically per bit as well, but since we did the math in bytes, we'll say cost per byte. And so this is going to be your dollars, and then I guess the byte size. So this is the size of the drive, okay? And then this is the cost per bit over here, actually, if we're looking at this as a proper Well, this is just cost, because the math is when you put them together. But yeah, this is just the cost of the drive, and this is the size of the drive. And you can see here that the cost goes down. Well, the size of the drive, this, if we're looking at the graph as this, then this is really more actually what I had before. So cost per bit, and then yeah, the labels wouldn't work. Otherwise, this thing doesn't. Hopefully this is making sense to you guys. Essentially, what I'm trying to make a point is that sometimes a single drive solution is not the way, because it'll be more expensive. And yes, there might be single drive solutions that are like, I'm sure somewhere out there there's like a 20 terabyte hard drive, or well, that's actually possible, but a 20, like maybe there's a 20 terabyte like SSD or something out there, and it's like an R&D. That's going to be what's going to be available for sale maybe in a couple of, maybe 5 years or something like that. And that's like the R&D that's eventually going to come out, which at some point in time, when we were buying a 512 gigabyte SSD, I'm sure they were already working on like a 2 terabyte SSD, and that was that's because of the next generation that's going to come out. But if such an item was for sale as a sort of prototype, it would be extremely expensive to produce, and that is why bringing the cost down to the consumer is what takes time before it actually is sold, right? So, it's if you're looking at graphics cards, it's the same thing. You got the latest and best graphics card that just came out is going to be the most expensive, but technically there's even something better out there in R&D, which is not even for sale yet because they become prohibitively inexpensive. One time I went to CES and I saw like a 8K TV back like a couple of years ago, and the manufacturing cost of that was extremely insane, like $20,000 or $25,000 or something like that. And obviously they're not going to put that for sale, and if they do, it's going to be some sort of like prototype sale where they're not for the general public per se. But the goal is that at some point they're going to keep working on the technology, bring the price down, and eventually it's going to reach the consumer. But of course, to get there, they first have to prototype, right? And that takes money. So yeah. So anyways, that's kind of just what I'm trying to go with this. I hope I did the math right when I did the division here. Let me triple check, because I might have screwed up the division. So this should have been, because I did 500 billion there, but I don't know if that was the right. We're doing in megabytes, right? So really here, I think I might have screwed that up. This should have been 500,000 if we're doing it per megabytes, and I think I did 500 million. So let me just triple check that I did the math there, right? Because since you guys are not watching this live, then if I make a mistake, you guys help me out when I'm teaching live, because if I make a little math typo, someone will catch it. But when you're doing this pre-recorded, we do lose that ability for you guys to catch a mistake. So no, I did do the math right. Okay, perfect. So that's for 500, it's that, and then for one, it's that. Let's see, for 1 terabyte, it would be 7300. That does look suspicious now. Let's see if we got 1 terabyte. Oh, no, it doesn't. No, okay, we're good. Okay, perfect. Yeah, so everything is fine. The math is right. So for example, if we're doing the 4 terabyte hard drive, we're doing it divided by 17700, which gives us 225 megabytes per cent. And then this one, it is indeed, I don't know when I guess it's because I was first tolling bytes before I switched it to 2 megabytes, right? So in that scenario here, we have 500,000 divided by $56, I think, 00, and that gives us 89. So yeah, okay, so the math is right now. Perfect. Triple check that. So anyways, what it turns out the situation here is that if, the original thing was our boss told us to buy, how much did I say? I think 20 or 32 terabyte. So in the scenario here, because the biggest one available for sale was the cheapest one, then we basically just kind of Lego it together by getting I think that was the 6th one was the biggest one. So we would have to end up getting probably five of those, that would give us 30, and then probably buying one of these, you know, and calling it a day. Alternatively, we could try to do the math. This is known as the Knapsack Problem, actually, which is NP complete, but this is an easy version of that. But anyways, we basically try to make a combination of the cheapest mix of them, which would probably be including basically the biggest one here, and then a mixture of the smaller ones to fill up the last remaining bits. Because I mean, the cheapest here would be, if we have to get 30 terabytes, then no questions asked, we're just going to get a bunch of these. But for the last 2 bytes, you know, is it cheaper to buy one of this, or is it cheaper to mix and match? And I think it'll probably end up being cheaper to buy probably one of these along with the 6 terabytes. And also that keeps the amount of drives low. And that's a good point, you know, to bring up next here. Sometimes it's not just about the number of drives, you know, because imagine that you went to some place where like there was a bunch of 500 gigabyte hard drives that were really cheap. They were selling it to you for like $2 each, you know, because they didn't want them anymore because they're so tiny. And you're like, wow, the cost per bit is insanely low. And you're like, just buy like 50 of those. But then you run into another problem. Where are you going to plug 50 of those? Because you want to have them actively available because your boss wants them to be like on the cloud, you know. And so now you got to figure out how to get some sort of switchboard or a motherboard that can take 50 SATA ports to connect 50 hard drives. So that also becomes a problem, right? So in the perfect world, we want one single drive that is like insanely big, and we can just plug it in and call it a day and not have to worry about organizing information, because like that's the other thing. Suppose you end up buying, you know, we said we're going to buy 5 of the 6 terabytes and then probably 1 of the 2 terabytes, right? And so how are you going to store information? You're going to store some here, you're going to store some here. What are you going to store on each, right? Are you going to just fill them up like one is full, now go to the next one and so on? You got to have some sort of organization to this, right? And so in the book, you know, they introduce a concept that was introduced, I suppose, by Berkeley. And it was a paper written in, I think, the 90s or the 80s. Let me see. 88. So it was a. So think about that. Rate is that old. So in the University of California at Berkeley in 88, they wrote a paper introducing the concept of, you know, okay, we're trying to have a lot of space, but we're going to be forced to kind of not go with a single large expensive disk, which is what SLED stands for. You know, there is no such 32 terabyte SSD or hard drive. Well, hard drive there might be, but easily accessible there isn't. And so our only alternative is going to have to be to buy a bunch of the smaller sized ones. But, you know, can we take advantage of the fact that we have multiple drives when it comes to trying to speed up the system, you know? Because here's the thing. Think about it this way. Suppose that we make a simpler example of this. We have 2 hard drives, okay? And they're each 1 terabyte. Here's the thing. Suppose that we are writing a file to them. If we're writing a file to them, you know, and that file is maybe 1 gigabyte, the time it takes to write it to this disk is going to depend, as we talked about last time. You know, it's spinning. You have to go with the seek time and then wait for the thing to spin around, which is your rotational latency, and then actually writing it down. You know, the time it takes for you to copy the data, which is going to, you know, we're assuming that this thing can write as fast as it's spinning. So probably, it's a matter of how long it takes to spin to enough area of the drive to write enough data, right? But it's still relatively slow. And so here's the thing. If you're trying to write a lot of information quickly, you can actually take advantage of the fact that you have 2 drives, because here's the thing, they each can be writing at the same time, right? So why not just take the data and actually split it into 2 pieces of 512, well, I keep thinking power of 2, but in this case it actually 500 megabytes each, right? So half a terabyte each. And now that we split it, why not put one of them in this drive and then put one in this drive? You know? And that's the thing. If it would normally take you about let's just exaggerate and say it takes you 2 milliseconds to write. Well, actually, this is not an exaggeration. But let's say it takes you 2 milliseconds to write a 1 gigabyte file to a single drive. you know, and it only takes 1 millisecond to write half a gigabyte, so 500 megabytes, right? If that is the case, then I can actually write this faster by writing to each of these half the time. It's half of the data, because then it's going to take 1 millisecond to write both of the pieces, because they're writing it at the same time. You know, if we can do that, achieve that, you know, plus or minus a couple of picoseconds or whatnot for the seek and latency and whatnot, right? Okay, but that's kind of needed either way. So we can save time by being able to write. Furthermore, if we want to read this data back up, so if say we want to read it back into main memory, so other way around, we can actually access the data quicker, because, you know, normally, again, ignoring seek and latency time and whatnot, if we have the file in one disk, then we have to copy it over, and, you know, we gotta wait for it to keep spinning until we get all the data, right? But if it's in 2 disks, then we can read it at the same time from both, and then basically, you know, put it all in memory. And again, the bottleneck here is the drive. The memory can take as much data as necessary. It could take all the 1 gigabyte at once, but the bottleneck is going to be able to transfer the data into main memory. And so by splitting it into these 2 drives, we can basically read it in half the time, you know, pretty much. Again, we're cutting a little bit of the details in this, but pretty much this is a good summary of why this would be pretty much twice as fast for both reading and writing. So that's what the people at Berkeley were like thinking about, and they came up with the idea of what is initially what RAID stood for, which was redundant array of inexpensive. So yes, they were all about the money, I guess. Inexpensive disks, in comparison to the other term which they defined, which was single large expensive disk, which was SLED. So that's single, which is no longer really a term that's really used. But, you know, that's only because nowadays the disks that they use in RAID configurations are pretty much the same disks that you would use in a normal hard drive. I mean, yeah, sure, there's like data center hard drives and marketing schemes, but for all intents and purposes, they can be using the same drives that you're using. So that term kind of disappeared, but this term kind of remained. However, nowadays, what RAID really stands for, at some point in time, they were like, wow, this is not really a cool term to use. They went ahead and replaced it with redundant array of independent disks. So that's what RAID stands for today, okay? So at some point they went ahead and changed the term. And this is like an international agreement, because here's the thing. What the people said at Berkeley, in addition to saying like, hey, we can actually split the writing and reading, there's a side effect that happens to this, okay? So here's the issue. This is great. You know, half the time to read and write, you know, it's a big gain as everything, and there's not really a cost to this really, except for there's also a higher risk, because here's the thing. If you're keeping the data, suppose that you have 2 disks, but you're writing, let's say, 1 gigabyte file here and 1 gigabyte file here, right? And they're independent files. Like this is a I don't know, this is a data set for natural language processing, and this is a movie, right? This may be one of my live streams. You download it from YouTube, and you're going to watch it later, okay? So if one of these drives fail, because again, hard drives are mechanical things, there's spinning involved, and all mechanical parts are doomed to fail given enough time. That's kind of just a fact of life, right? So at some point in time, hopefully not soon, and more than likely not soon actually, one of these hard drives may fail for any reason or the other. So if one of them fails, suppose that this guy fails, and so bam, you lose all the information. I mean, you might be able to recover it, but at the time being, you lost it, okay? Until you can send it to some team who can try to extract the information by maybe changing the head or seeing what happened with the drive, right? And more likely they will be able to recover it unless like that drive exploded or lit on fire, or a big magnet like smashed into it or something. Other than that, they'll be able to pretty much recover it. But in the meantime, you know, the customers needed the data, and now they're like angry at you, right? They're like, we don't want to wait 2 months for you to like send this out to Intel or somebody to, not Intel, but like, I don't know, to Seagate or Western Digital to recover the drive. They want their information now, right? So in the meantime, you're going to have a bunch of angry customers, and there's still a risk that you might not recover all the information. You know, some of it might be gone forever. And so the one thing, sort of the one okay or positive thing about this is that while you lost my live stream, which is a very sad thing, and you know I won't forgive you for that, the NLP dataset is perfectly safe because the entire dataset was contained here. Okay, so while you did lose one drive, you lost 1 gigabyte of data. The other 1 gigabyte of data is perfectly safe, you know, until at least this drive fails in the future. But for now, it's safe. Here's the thing with this scenario here. With this scenario, we weren't just, you know, putting data in 2 drives, but we're putting the same individual data in 2 drives. So this is more of like taking the let's say we're taking the live stream, and we're splitting the file. And how we're splitting it is not as clean as just saying half of the file. But even if it is, we are taking half of a file and putting it in one drive and in the other one. The problem with doing this is that if one of the drives fails, we've actually lost data from both of the drives, because the live stream file, you know, it's just a bunch of zeros and ones, and it's not as easy. While some files, like, you know, a text file is indeed just one file, and you can easily split it, and you can read the first half without the second half. You know, if there's a file that has like compression or has other pieces to it, you actually need the full file to be able to actually access the data. And if that is the case, if you lost half of it, you might as well would have lost both drives, because one half is useless. You can think of it that way. Like if it's a zip file, for example, and that file is compressed or is encrypted, you need the entire file to be able to decrypt it. And so now you basically lost, not even though you've only lost one of the drives, for all intents and purposes, you've lost both drives. So this is sort of the negative side to splitting data. Obviously, if you can just you know, split different files to each drive, this doesn't happen. But then you lose the efficiency idea, because the idea is, if I'm writing, for example, the live stream, you know, if I'm writing the live stream to 2 drives, I'm only going to gain the writing efficiency if I'm actually splitting the one file I'm writing into multiple drives. Obviously, if I have multiple files to write, then yeah, I can go ahead and send some files here and some files here. But that only works if it's multiple files. If it's one big file, then you got to split it. And then that's when this problem arises, where if one of the drives fails, you lose the entire array of them. So the Berkeley people, in addition to suggesting like, hey, this is a cool idea, they also suggested a solution to this. And that's what the different rates are going to be. Are going to be different solutions to the risk associated with splitting data over multiple drives, while still having a chance of recovering the data if at least one of the drives is gone. And so RAID 0 to RAID 6 are going to be different standards that I think pretty much they came up with all of them, but I might be mistaken. Other people might have come up with other ones. They at least wrote 2 papers on this. The first one was in '88, but the second paper was written later on in like the '90s. I'm not 100% sure on the history of that. But the point is that they came up with 5, and that's not 6, because you'll see one of these isn't really RAID. But they came up with 5 approaches to be able to have the gained efficiency of splitting data into multiple drives, but also having some sort of redundancy where if one drive fails, then we will not lose the entire array of them. And so, as you can guess, since we talked about it quite recently, one of the ways that we're going to do this is with Parity Bits. So we're going to use Parity Bits to basically, like Hamming code actually is want to be one of them, although that's not the best one, but that's one of them. Is going to be the way that we can do error correction and error detection, right? Because we know with Hamming code, we can correct errors automatically if it's one error, whether it's the parity bit or the actual data bit. And we can also have the system that has the single error correction, double error detection, which has an extra parity bit, which basically makes the entire mixture of checks bits and data bits even or odd, right? So if it's odd, that's a 1 in that extra bit, and if it's even, then it puts a 0. And that odd or even parity bit system is actually going to be one of the ways that we're going to use in RAID. And that will help us a lot to basically correct things. And so, yeah, that's pretty much what we're going to do. So the reason I say that there's only 5 of these that are really using the system is because let's talk about the first scenario, which is going to be RAID 1 first. Let's talk about RAID 1. That's the easy one. So RAID 1, all you're doing for the data is you're mirroring the data. So if this 1 terabyte hard drive has data in it, you're putting the exact same data in this one. And so if you have a 1 gigabyte file, it's going to be in both drives. So first of all, you get no efficiency gain in writing, right? Because yeah, you're writing to both of them at the same time, but you're still writing the same information. So assuming that they're the exact same drive, and they were positioned at the exact same spot, like the same, both of the heads were aiming at the exact same sector. So like, let's say this one's aiming here and the other one's aiming to the exact same spot. Then in theory, it should take them the exact same time to write, right? And if not, then it's just going to be a very small difference. In the case that like the heads were a different spot or the drive decides to do something differently for some reason. But ultimately, you're not going to gain any efficiency with writing. So then you're like, okay, then why use this at all? Well, because it's not all about writing. It's a two-way road here. We have writing and reading. With reading, we will have an efficiency gain because if we are reading the information, because we know that the disks are mirrored, we can say, okay, you read this part, and then you read this part. And ultimately, by splitting the reading to from the different drives, you know, we can read in half the time because we can read in like half the information from here, and then we can read the other half here at the same time and put it in main memory. And so RAID 1, it's basically just mirroring the drives, which is basically having duplicate drives, but you get the efficiency of basically being able to read in twice this time, okay? So for RAID 1, you need twice the number of disks that you would normally need if you were just having information stored once. And it is great for reading in essentially. You know, you can read in half the time, twice that of a single disk for read. But you get no efficiency gain for writing. It takes the same amount of time. Okay? So yeah, that's pretty much what RAID 1 is. And the advantage of RAID 1 is that because things are mirrored, if one of the drives does fail, so let's say that this guy just died, that's okay because you have another one with basically the identical thing. So if that happens, what you do is you take out the bad drive from the system. The system does slow down a little bit while you do that because now your reading is kind of limited to just one of them. But then when you put the new one, then you can just have software that copies it over and then you're back in business, right? So it has that benefit that if one of the drives fails, you know, you get an alert, and because you know it matches them and it sees that you can't write to them or things don't match, and then that you can just go ahead and swap it out, and you only have a sort of an efficiency loss while you're swapping it, but you don't have any data loss. Now, if you lose both drives, then you know, bad luck. You've lost the information, right? And so, if you wanted to do RAID 1 with like 5 drives, you know. Well, in that case, you will need 10 of them because you need a mirror for each of the drives, right? So each one's going to have a mirror. So let's do an example with just 2. In that case, you need 2 more for the mirror, right? So you basically just always need twice the size. Now, what is RAID 1 used for? On the book, there's a little chart, which I'll talk about as I go through each of these. But one of the most, the popular uses is for accounting, payroll, financing, and applications that require high availability of the data. And yeah, basically there's a lot of overhead involved for this, and it's quite inefficient because of the copying, but you still get the efficiency with the reading, okay? So that is basically what RAID 1 is going to be. So now let's go back to talking about RAID 0. So this is the only one that doesn't involve some sort of parity bits, okay? So that's why it's not really a kind of a RAID thing, because when we think about RAID, we think about parity bits and whatnot. But yeah, that's out there. So anyways, talking about RAID 0. Okay, I'll drink some water. And by the way, there's some. This is coming from chapter 7, section I think 2, and there's a lot of nice pictures there and charts that I recommend that you check out. Very quickly, I will switch over so you can see that. So this is, for example, one of the charts in the book that has all the categories and a lot of the little details. Very good thing to remember and to have accessible, like if you were dealing with RAID or in the tests and things like that. There's also another chart in the book called RAID comparison, which is also quite nice, as it does tell you what each drive is good for. I can't see my mouse. Here we go. Okay. So the other chart is like down here. That one is also very useful in the book, so check that out as well. Table 7.4 on pages 200 and, well, it says right there, 230 to 31, and also the other one is on page 223. So definitely check those tables out so you're watching the lecture, if you because I have the iPad open, but you kind of want to have those handy as well, because a lot of the information I'm talking about is coming from those charts. So that's one of the charts that's actually really nice in the book. So definitely, print that chart out and put it in your wall if you want for the test or something. So yeah, okay. And there's also pictures as well of the different setups. So if you look at those pictures, what do those pictures look like here? So you can see, I'm going to be talking about these pictures like this, okay? I'll be drawing them as well, but just so you are aware of that. So looking at RAID 0. By the way, let me define one term that I just saw when looking at those pictures, and the term is going to be strip and stripping, okay? And what stripping is basically taking your data and splitting it into tiny pieces. So like when we did the splitting of the data here into 2 pieces here, you know, the 1 gigabyte file that we split into 500 megabytes, you can think of that as a strip, because we basically store 1 strip of the file in here. So this is like, you can think of it as like strip 1, and then you have strip 2. Okay, so that concept of stripping is going to come in very, very useful for the rest of these. So with RAID 0, that actually, well, technically RAID 0 doesn't quite have parity bits as well. So I guess I lied earlier when I said that. So yes. So what RAID 0 will do is it's going to do actually what we were just doing before. Actually, yeah. So this would actually be kind of like an example of RAID 0. So RAID 0, you know, we're gonna do the example that we have 4 hard drives. Okay, we'll do 3 because the book says 4, so to go different than the book. So if we have a file that, you know, is made up of whatever, 1 gigabyte or whatever, suppose that we are splitting the file into tiny little pieces, and these strips are going to be a defined size that you can kind of sort of pick, but ideally you want them to be relatively small, but not at the byte level. Okay, it's going to be little blocks. Okay, and so you split the file into strips 1, 2, 3, 4, 5, 6, 7, and 8. Okay, and so typically the reason why they go with powers of 2 for the drives is because of the how, so that you can split things nicely. Because I have things not like this, and let's just say we have 1 more strip, so it splits nicely. You ideally want to split this into a multiple of the number of drives that you have. So in the book they split the files into 15 pieces. Well, technically 16, 0 to 15, you know, because they have basically 4 drives, and that makes it easy because you store 4 strips per drive. But here in my scenario with 3 drives, we're going to split it into 3 each. Okay, and so what you do is you're going to store into each of these sort of like a pieces of this. So you're going to have like piece 1 here, piece 2 here, and piece 3 here, because you can write those at the same time. So in the time it takes you to write 1 strip, you'll be writing 3. And then for the next 3, you're going to do the same thing. So you're going to write stripe or strip here 4, 5, and 6, which will also take you time, the amount of time it took you to write 1 strip. And then you're going to do the same for the last 3, which is 7, 8, and 9. So that means that this drive contains the first part of the file, then kind of like in the middle of the file, and then near the end of the file. So it has strips 1, 4, and 7. Okay? And so by doing this, we the time it takes to write this into the drives would be the time it took to just write 3 pieces. So we basically cut the writing time in 3, divide in the factor of 3. So if it would have taken us 3 seconds to do it, now it's going to take us 1 second to do it. So that's a nice big efficiency gain. Furthermore, if we want to read from this, same thing. We're just going to read all the strips and kind of put them back together here in the main memory. Of course, we know how we split things. We know that we put strips 1, 4, and 7 in drive 1. So we know that we have to assemble them in that order. So we're like, okay, put this one here and then leave space to put 4 and then leave space to put 7, because when we put, the second drive goes here and then here and so on, right? So you Lego them back together, and you're also able to read in 3 times as fast, because you basically only need time to read 3 strips, and then just basically as long as you read them concurrently, you'll be able to get all the information back in again 3 times as fast. And so that's basically how RAID 0 works, which again is actually kind of what I was showing you above here by splitting it. Except in this case I put 2 drives, whereas here I'm putting 3 drives, and I kind of defined the whole idea of a strip. Yet again, the big risk about this is if one of the drive fails, so like if this guy just dies, it's a defective drive and it died early, you lose the entire data because you can't build it back together now. You're missing pieces all over the place. So like, it's not like you just split it evenly, like you split, you put the first half of the file here, or the first third, and then the second third, and then the third third. No. You split it into pieces so much that like, if we're trying to reconstruct the data, here we have S1, S2, S3, S4, S5, S6, S7, 8, and 9. We've lost essentially, we have all the data still. We have these, and then 4, 5, and then these we have, and we've lost this part of the data, this part of the data, and this part of the data. So that because we lost the data all over the place, that file is corrupted and it's gone. Like GG, bye file, because it is indeed gone forever. So that's bad, right? But it's like we like to live dangerously, and so because of that, we want to have that 3 times increased read and write at the risk of, yes, we might lose data. So who would want to use this, you might ask? Well, let's put it this way. First of all, the failure of just one drive will result in the entire data loss of the entire thing. So you might as well have lost the entire array of 3 drives, because with one drive lost, everything is gone. So, and it's also a very easy thing to implement. As you can see, you just have to figure out how to split things evenly, and then the same way you split them, you use that algorithm backwards to put them back together. So it's easy to implement, and because there's no parity bit or anything like that, there's no computation you got to do. You're literally just like, it's like giving out cards in a poker game. You're just splitting them out, and it's all good to go. And you got nice read and write gain to this, right? This is known as a non-redundant configuration, because there's no redundancy, as in like when it fails, it really fails, right? And so who would want to use this? Well, suppose that you're doing some sort of processing, like a supercomputer, or video production editing, or image editing, or any application that requires a lot of read and writing. But it's only temporarily that you're using this. So like, for example, suppose you're going to render a movie. So you transfer in the files in here to be able to do that. And then when you finish that, you save them somewhere else where it's actually safer. So you don't really care too much about if the thing dies halfway, because you probably have the data somewhere else as well. So you're only really using it here, but it's not your only copy of the data. So, you might have it somewhere else. So in that case, it's not that big of a problem. If you're doing like a data center and you're processing like terabytes upon terabytes of data, and you really need to process it quicker, you might be okay with risking that data, because again, it's not mission critical if you do lose the data, but you really care more about it. Obviously, in the best case scenario, you want it to be super fast, and you also want it to be super secure, right? So that, of course, the equivalent of that scenario is going to be the most expensive scenario. So you have to, decide what you want to do. Obviously, if you were to able to make something like RAID 0 and RAID 1, then you would have all of the benefits of RAID 0 while having a backup of it, because you have some sort of mirror system of that, right? So that would be sort of like the ideal scenario. But again, that would be very expensive to do. So that's not really ever done at all. So, but anyways, there's still a legitimate usage of RAID 0 when this stuff is not mission critical. And I mean, let's think about it this way. Yes, there is a higher risk of failure because, again, if you buy 10 drives at the same time, you expect them to last all about the same time. Yeah, sure, one of them will die a little bit early, but they should be all about the same. That's sort of the ideal. But the reality of thing is that the more drives you have, the more exposed you are to the probability of one of the drives coming out defective, right? So like if they say the percentage of defective drive is, let's just exaggerate because it's not this high, but let's just say that it was 1% chance of failure, okay? Like early failure, like early death, like it fails within the first year, okay? If you only buy one drive, you're only exposed to that 1% chance of failure. Pretty low odds. But let's say you got 100 drives. Or even more, you have 1,000 drives, okay? You have 1,000 drives in your system. In that case, the statistics say that you should expect about 10 of these to fail. But here's the thing, now you're kind of living dangerously here because you have so many drives that now the statistics are against you that, yeah, one of the drives will probably fail. And if you're relying on the entire thing being RAID 0, that will kill the entire array. So now you're playing with fire, right? So it's really a matter of trying to figure out, cost benefit in terms of that. So, what if we want to be able to have this whole gain efficiency of multiple drives, but we don't want to do mirroring because that's a lot of drives that we need, and this is very dangerous. So the next sort of RAID that I'm going to show you is is basically kind of a middle ground between these two scenarios where we are going to be separating the data into strips, but we're going to be adding some form of redundancy to this so that if one of the drives fail, we don't just lose everything, okay? So the first one we're going to talk about is going to be RAID 2. So this RAID 0 is typically known as just stripping, by the way. That's the nickname for it. Striping. I don't know if you call it striping or stripping. There's only one P, so I do not know, okay? So now let's talk about RAID 2. So RAID 2 is going to be the same thing per se as RAID's sort of 0 in the sense that we're going to be splitting data, but we're actually going to be splitting it at the bit level, okay? Could technically do it byte level, I suppose, but in reality, I think it's usually done at the bit level. Yeah, because you can do the zeros and ones. Yeah. So it has to be done at the bit level. So in that case, we are gonna split our data in this sort of format of like if everything is stored in like 32. Well, let's say everything is stored in 4 bits at a time. Then let's say that we're storing the number 010, 0101. Then what we do is we basically line up all the read heads so they're all going to the same spot, and in all of the drives in the same location, we're going to store 1 bit of the data. So like, let's say they're all storing it right there where that line is, okay? So what we do is we put a 0 on that one, a 1 on that one, a 0 on that one, 1 on that one. And if it's somewhere else when you got to store more data, let's say we want to store 1110, let's actually do 1101, then maybe that's down here. Again, it could be anywhere in the drive. We're not specifying that it has to be in some specific order or like accounting order. It's just that wherever it is on the drive, they're all writing the same thing. So, if you were to look at all the drives under like an X-ray or something, and you were to see what is actually written on it or not, they would all look basically the same locations used with just different values in it. Because some of them might have zeros, some of them have ones, okay? And so, if we did this is kind of still, if you do it this way, it's kind of like a RAID 0, but we're doing it at the level of bits instead of stripes. So the big difference here is going to be that we are not just storing bits, but we're also storing check bits. And so RAID 2 is basically going to be using Hamming code for error correction. And you guys remember Hamming code, so I'm not going to go into detail of that. Go back and watch that video. It was, I think, like 2 videos ago that we did Hamming code. And so you can definitely check that out. But essentially, with Hamming code, we're going to have our check bits. So in this scenario, we would have technically 3 check bits for this number of data, right? Remember, if you're able to store 4 numbers, then you essentially would need 3 check bits for this. If you store 8 numbers or less, anywhere from 5 to 8, you would need an extra check bit as well. Yeah, so anyways, these check bits are going to work the same way that we talked about in how they're actually calculated, right? So we're using XOR for being able to compute them. And also, we know that if one of these bits is wrong, then when we do our XORing, that is going to tell us that is wrong, and we can also correct it as well, right? So it's not just the fact that we know that something is wrong, but we also correct it. And so here's the really cool thing about this. If one of these drives completely dies, so like this guy just literally lit on fire and melted down, then we're okay, because we can use XOR to rebuild it on the fly, right? So in this case, let's just say that, well, I don't really want to do Hamming code on this to figure out what these bits are, but let's just say that the check bits for this were something like 101 or something. And so when we do the check bitting, we know that this is gonna, in backwards it would tell us something like, if this is position 1, then this is gonna give us this, which when we flip it tells us, actually would give us it would give us once we flip it, it gives us 1, so it tells us that the problem is in this drive, right? But not just that, we know that because that's the problem, we can recover it. So and the way we know that if it's just failed in 1 bit, then it means we gotta, like, if we're reading the first line, we got a 0 out of this. But if the whole thing exploded, so we don't even know what's there, then we know that is a drive that's wrong. So then we can use Hamming code to figure out what it should be, because we can make a guess. We can say, like, it's probably a 0, and then we do Hamming code and it tells us that it's wrong, then it becomes a 1, and now it's good, right? So we can use Hamming code to rebuild this drive. So what we do is, once we take out the broken drive, we put in a brand new drive, and then we can use XOR operation to build it back to this using Hamming code. So we run Hamming code on the entire drive to figure out what each of the bits has. Furthermore, while we're in the process of doing that, our data center will slow down a little bit because there is a little bit of XORing going on, but it's not too bad. But we can still access all of the data because we can rebuild it on the fly by using the error correction that Hamming code allows us, right? And furthermore, because Hamming code allows us to have second, if we had the extra check bit, we could do that double error detection, not correction. But again, hopefully we quickly replace the drive before another one fails, and also rebuild it. Okay, and so the number of disks required is going to be n plus m. I never set it for the rate 0, but that's just, you need the number of drives. It's just whatever number of splits you want to do. But in this one, we need a number of splits in addition to the number of check bits, which is going to be m, which again you can figure out with Hamming code how many you need based on the rule of that, which is powers of 2s. And so the data availability is much higher than a single disk, and it's quite comparable to the other RAIDs that we're going to talk about, 3, 4, and 5. But it's overkill. Let's put it that. I think even the book uses the word overkill. It's overkill to have these number of check bits for this. It's just way too much space that we're wasting on this. And yes, I know that once you get big enough with Hamming code, you only have about 3% of the space being used for the check bits. Once you have like 200 drives or 256 drives. But it's still a lot of drives that you have to use for the check bits. Now, in terms of reading and writing, you add in an extra level of complexity here, because you need to compute what the check bits are when you're writing something. So if I'm writing the number 0101, I need to actually, I was lazy right now. I told you, like, I didn't want to figure out what these were, right? Well, the computer does, and they have to do XOR operations on the data to figure out what those check bits are going to be. And so that takes time. So it's a little bit inefficient in that sense. However, you do gain of approximately twice the ability to read and write when it's a small file, and when it's a big file, you definitely got a lot of efficiency, almost in the level of RAID 0, because again, in this scenario, I'm splitting my data writing by 4 because I can write up 4 drives at the same time, and because they're all lined up, there shouldn't be a delay in one of them. So really, I'm cutting the writing speed by 4 minus the time it takes to compute the check bits. So that is going to take some time, yes, but that is a lot faster because you can do that in like, the CPUs can do that very fast, or maybe there's an embedded system that is in between the main memory and the hard drive that does all the RAID computing for the parity bits, And sometimes I do believe that the disks themselves have that built into them. So that can happen super, super fast. I'm sure they have little tiny pieces of cache or fast memory that can compute the parity bits on the fly really, really fast. And that would be like your RAID controller. I think that's what they're called, RAID controllers. And so you can set that up on the CPU, but if you buy a system that is meant to be for RAID and it already has the base and everything, so you just plug in the hard drives, there's going to be some sort of RAID controller that does this. So, writing into your hard drive is so slow that it's going to be almost insignificant the time it takes to do the parity bit computation. Okay, so really here, this is a really good solution, but the problem is it's just overkilling the number of drives you need. I mean, M plus M is just insane. And yes, I know, again, if you get enough drives, it's only about 3% loss of efficiency, but it's still a lot. I mean, it's still a lot of money. And companies don't, it turns out that no real commercial implementations are viable of this because of just how much cost you need for something like this. So while it's cool, it's not commercially viable. So people just kind of be like, yeah, that's fun, nice and fun, but yeah, we're not buying that many drives. So come up with a better idea. So yeah, that brings us into RAID 3. That looks weird. Let me try that again. Writing these, uppercase these, is just hard for me. I don't know why. It just feels weird. So yeah, insight into writing stuff. Okay, so this does have the ability to have parallel read and write. And RAID 3 is also going to have this ability. So let's talk about RAID 3. So RAID 3 is going to have a parity bit, but it's going to be more of like the odd or even parity bit. So if we're storing, it's still going to be on a bit level. So it's going to be just like this RAID 2, but instead of doing all the check bits, it's a simplified version where it just does the even or odd check bit. So what I mean by that is, if I'm going to go with 3 because the book has 4. Let's say that you're storing, the following information: 0, 1, 0, and maybe 1, 1, 1. Okay, and maybe 1, 0, 0. Okay, so you're storing those 3. So maybe this one gets stored here. Then the next one gets stored down here. It's still storing them in the same locations, so they're all lined up. It can be out of order, but still in the same location of the drive, right? So like, if it chooses to write something here for the next one, then yes, it'll do it all 3 of them in the same spot. But the next one could be here. There's no. I mean, yes, when you defragment and principal locality, you want to keep data together, but that's not part of what the standard for RAID is. And this is now an international standard as well. So which is useful because you want to have some sort of standard when drive manufacturers are trying to sell you these things. Okay, so yeah. So in this case, what we're going to have is we're going to have a parity bit that's just going to keep track of even or odd bit parity, which means that if we have 0, 1, 0 as our data, 1, 1, 1 as the other data, or 1, 0, 0 as the other data, it's just going to XOR them together, and then that is going to tell us basically whether you need to put one bit for odd or even. So this means that this will give us a 1, this will give us a 1. Are they all odd? I really try to make one even, and I think I just failed epically at that. So yeah. Okay, let's just say that the data was 0, 1, 1. In this case, the parity bit was 0. Okay, so I was trying to do that here, and then I just kind of stopped. So let's just do that, because I want to have at least one where it's 0. Again, I did go over parity bits. Before I even talk about Hamming code, I show you the odd or even version of it. That's what this is actually. It's a simplified version of this that's it's not perfect, but it's something. So what was the disadvantage though when we were talking about this? The disadvantage with this method of doing just odd or even check is that if there is an error in the data, you actually don't know where the error is, right? When we talked about even or odd parity, I said that, like, you know, yeah, sure. If you transmit this into another machine and you're expecting when you run an XOR on this to get a 0 and you end up getting a 1, then you know there's an error, but you don't know where that error is, right? So that was the problem. That was the reason why we use Hamming code, because Hamming code allows us to also know where the error is, whereas this does not, right? So here's the thing. We still have that problem here. So then you're like, you know, I want this to be redundant. You know, I want this to actually be like, not just to basically tell us that there's an error, right? Because, like, okay, great. If my drive explodes right now, if this drive explodes, so here, let's build the parity bits for this. So again, this now is 0 because it's 101. This one's a 1, and this one's a 1, right? So if, like, you know, this drive melts again, yeah, sure, I'm gonna run my XOR, and it's gonna be like, by the way, this guy's broken, and I'm like, duh, it's literally on fire. I know that. Thank you. But, like, how are you gonna help me to actually fix this, right? Because I'm not using Hamming code, and I know that Hamming code will hook me up with actually fixing this. But odd or even parity bits don't actually correct the error. They just tell you there's an error. So then you should be asking yourself, great, so what uses this when, yeah, sure. How do I know there's an error? I can just go look at the rack and see which drive is literally on fire, right? So, like, this is not useless for us. Well, here's the thing though. You should have been patient with the machine. It wasn't just trying to tell you that this was the problem. But here's the thing. Actually, it doesn't even tell you there's a problem, right? It just tells you, like, oh, by the way, some drive is wrong because the parity bits are wrong. It doesn't even tell you what. But here's the thing. If you can find out which drive is wrong, then you can rebuild that drive using the single odd or even parity bit. Because here's the thing. You know, this drive exploded. Parity bit is panicking because it's like, oh my god, we have now 1 0 0, which is basically odd, you know, so it's going to give you a 1. But here's the thing. It will tell you that something is wrong. It doesn't know where, what, how, but you can actually use the parity bit XORing to rebuild the missing drive, because you know that this is the drive that exploded. You know that because you see that it melted out, you know. So you know that this is 1 0 missing bit and then that. And you know that because you ran the parity on this, that this is supposed to give you 0 with the XOR, right? So all you gotta do to figure out what this should give you is just run XOR on the remainder of the bits. So run XOR on the 1 0 1. And if you run XOR on that, you know, this, you know, remember 1 0 or 0 1 in XOR gives you a 1, and then 0 0 or 1 1 give you a 0. So if you run XOR on this, this will give you 1, and then sorry, I ran on the wrong value. If you run XOR on 1 0 0 0, which is what we're running it on, and again we have too many digits there. This one just like that. Then you will see that this gives us a 1 here, and then 1 and 0 give us a 1 again. Okay? So if you run XOR on the remainder of the values, and you know that this is supposed to give you even, then you can actually use that value that you just XOR to rebuild the missing bit. So if you do, again, for the other one, it's 0 1 missing bit, and then we have a 1 here. So again, this is supposed to be even, right? So basically the question is, what do we put here so that this remains even? Okay? And if we run this on this right now, you know, let's say we put a 1 there, then this will return us a 1, right? That's not an even value. So this has to be a 0, because when we did the parity bit, we were supposed to get an even number. So that's how you fix that. Again, that's the conceptual part. But if you just want to know the mechanical way, you just XOR it. So you do 0 1 XOR, that gives you a 1. And then you got another 1 there, that gives you a 0. So the XOR of 0 1 1, which are the only digits you have available, 0 1 1, is just going to give you back a 0. And that's exactly what that is. So while the odd or even bit can't tell you where the error is, if you know where the error is, you can use that parity bit to rebuild that drive. And so that's really cool, because here's the thing. It doesn't matter how many drives you have. So n can be whatever you want. You just need to add one extra drive for that odd or even parity bit. Now, let's say that what fails is actually the parity bit drive. Is that a problem? Not quite, because you can treat it the same way. You can just run the XOR and see if it's even or odd, and then you can rebuild the parity drive as well. So this is known as bit interleave parity. And it's basically the data availability is much higher than the single disk. It's comparable to 2, 4, and 5. And it's highest of all of the alternatives to that we have here. So you still have the ability to write really fast. You're still splitting it by 4 and whatnot. For reading in, however, you get about twice the size of a single disk and for small files. And it's great. You only really got to compute one parity bit as well. So that's a really fast operation. You just XOR everything together and build that. And if your drive explodes and fails, you take it out. And then in the meantime, the system can still work because it can just rebuild it on the fly. But when you put in the new drive, it will rebuild the entire drive and then recompute any parity bits. Now here's the only problem though. You want to make sure you don't screw it up, because if you're writing data to the drive, you don't have the drive right now. So like, suppose that you're writing to it a bunch of zeros actually, just 3 zeros to this thing, okay? So you compute your parity bit and you see that it's supposed to be a 0 as well. But the thing is, you can't write to this. So you're gonna pretend you write into it just so you can compute the parity bit, so that if later on you need it, you can access it. So you can still use the system by writing and reading into it. It's just it's gonna be a little bit slower because you gotta compute that on the fly. And also you risk that if another drive fails, so if a second drive fails, then yes, everything is gone. You lose the entire array. Okay. The only place that's gonna save you for multiple drive failures is really going to be a mirrored mode, where you have more than one duplicate of the mirror. So, yeah, basically you're screwed. Or if you had the Hamming code that had like extra check bits, I suppose, or something. Or actually, no, the last mode that I'm going to show you, I think allows you to have double failures. Yeah, that's right. So RAID 6 will allow you to have that. So yeah. So far, even Hamming code only allows you to have one error. And again, it'll do a good job at detecting where that error is automatically. Whereas here, you have to have a physical knowledge. If a drive fails with RAID 3 and you don't actually see it, because like, okay, I know I'm exaggerating when I say the RAID catches on fire, but the reality of thing is you might actually not be aware of which one failed. If you don't see that, then you're going to have to go on a little bit of a hunt to figure out which drive failed, because the parity bit is not going to tell you where it failed. With the Hamming code it will, and it's very quick and easy. But with this one, it's more of like, well, we know a drive failed, but time to go in a hunt and see which one it is. More than likely, though, typically when a drive fails, it just has catastrophic failure. So you know where it is, and that's typically what happens. But that is a potential risk here, that if the drive is like partially failing, then that's going to be a bit of an issue, because you won't really know what's up and where the drive is. So anyways, who uses RAID 3? Video production and streaming, image editing, video processing, any application that requires a high throw of data going in and out. And the controller design is actually very complex, because you're doing it at the bit level, and that can be quite a bit of a pain. But it's good. It's not used as much because the other method is kind of better, but no cloud services are going to use this. The one that's going to be kind of cool is going to be 5. That's the one that we're really the one that you should really know, because that's the one that's really going to be used in like data centers and stuff. But RAID 3 is cool. It's just that it's at the bit level, and the bit level involves a lot of complex circuitry, because you got to have all these drives synchronized, running in the same spots, and that synchronization is a pain, and single bit writing can be just bad and difficult. Yeah. So anyways, let's go ahead and move on to better pastures by talking about RAID 4. So RAID 4 is the exact same thing as RAID 3, literally copy paste, with the difference being that instead of being individual bits, it's going to be in blocks of data. Okay, that's literally the only difference. So that's pretty much it. That's it. So I'm gonna go ahead and switch over to the PowerPoint just to show you that, to kind of speed things up here. But here we have RAID 0 with the striping, non-redundant. RAID 1 has the mirror version, so you can see that it's striped, but it's mirrored of that. I guess I didn't quite mention that, but you can have that with RAID 1, where like the way that I showed it here in the iPad is that the entire file is copied over, but you can still do the striping with RAID 1. You just have to mirror all of the stripes as well into their own drives. So like you can see that it's literally a duplicate. Every drive has an exact duplicate, a mirror version of it. RAID 2 with the Hamming code, these are the bits, and then this is the check bits, data bits and check bits. And then RAID 3, as I said, is Interleave Parity, which again, if one of them fails, you do the odd, you do the XOR to figure out what the correct bit should be for that failed drive, as long as you know which of the drives failed. RAID 4 is going to be, like I said, the same thing as RAID 3, except the difference is going to be that the parity bit computation is done on an individual block. So so basically, instead of doing it by bits, it's doing it by blocks of data. That's pretty much the only difference that there is between RAIDs 3 and RAIDs 4. You can read the book to basically get more information about that. But really, the only kind of, I suppose, advantages to it over RAID 3 is going to be that is there really an advantage to that? There isn't any commercial applications on it, kind of like the Hamming code one. It's not commercially really viable because it basically, you get the worst write transaction rates, and it's very inefficient to rebuild the data on disk failure because of the way that the parity bit is done there. So it's not really very used a lot. So, but really, it's just so you're aware of it. It's basically the same thing as RAID 3, but by blocks. And building this parity block is quite a complicated process. Okay, so yeah, we'll go ahead and leave it at that. Also, I guess the biggest thing is this. Here's what happened. Here's an issue that appears with level 4 that is going to be a bigger problem, and that is when you're building the parity bit, the parity bit is dependent upon basically the other drives, right? So you have to know what's going to go in each information. So when you're writing when you're writing information to your system, you're writing stuff into these guys. You got to compute the parity bit and write here, right? But the parity bit actually becomes the bottleneck of the system. So you actually get a bottleneck when you're trying to actually create the parity bit. And that's actually a big issue of this system. That actually is one of the reasons why you kind of cut your writing time. And if you look at the chart here, you actually have lower than single disk for write. So you're actually writing slower than you would if you were writing to an individual drive. So really, really bad. You lose all efficiency and everything because of the bottleneck of the parity bit. Because here's the thing, you got to write to all these drives and then compute the parity bit. So it just becomes a big bottleneck because of that. So that actually brings us into RAID 5. RAID 5 is going to be where it's at. That's the one that's used by data centers and everything. So this guy is basically the same thing as 3, but in blocks. So I'll leave it here. Same as 3, but blocks instead of bits. And the big bottleneck is computing the parity bit. Okay? That drive, it's not just computing it actually, but actually computing it and writing it into the drive, into the parity bit drive. Okay, that really slows things down. So like sometimes like if you really wanted to implement this, you'd have to make that to be like some extremely fast drive, like I guess an SSD or something. I don't know. It's not really used in commercial applications because of that. So RAID 5 kind of solves those problems, and that's the one that's really worth talking about in detail. So RAID 5 is going to work like RAID 4, but it's going to split the parity bit into the other drives. So suppose that I have 4 drives, and before, you know, I could have this be a data drive, and then my parity bit drive, right? And if I'm splitting it into blocks, again, you could think of them as like strips as well. We got block 0, block 1, block 2, and then we have the parity bits for blocks 0 to 2, okay? And then we have block 3, block 4, block 5, and parity bits for 3 to 5. This would be RAID 4, okay? And this is the problem here is the bottleneck of computing that. So the way that we upgrade to RAID 5 is we actually store the parity bits in the other drives themselves. So what we're going to do is we are actually going to, if we have 4 drives, they're all going to be sort of data / parity drives. But what we're going to do is we're going to interleave, and I think that's the name of this. It's actually called interleave. The RAID 5 is called block level distributed parity. Yeah. So RAID 4 is block level parity. RAID 5 is block level distributed parity. And what you do is you're going to put the parity bits from 0 to 2 here. But then what I'm going to do is I am going to put, for example, blocks 4 here, blocks 5 here, and then parity bits for, trying to see if the math here is going to be okay. Yeah, this will be okay. Yeah, okay, so we'll put 4 and 5 here, and then we have block 6, block 7, and then we have the I don't like the fact that this one has 3. It's okay. Let's go with the one that's even numbers, because it bothers me that there's different sizes for the parity bits. So let's go ahead and put another drive in here just to make the divisions easier. I think that will no, actually that's okay. Always, I think what happens is always the first parity bit is going to be bigger, and then the other ones are going to be smaller. So yeah, let's stick to this because I don't want to use the one in the book, because you can look at that when you're on time, and that's an additional example that you can have. So this one's going to be parity bits 0 through 2, and then we have block 3, block 4, and then this does parity bits for 3 and 4, and then we have block 5, block 6, and then we got parity bits 5 and 6 here, block 7, block 8, and then parity bits for 7 and 8 here. And as you can see, it's sort of interleaving. So basically the parity bits are split over all of the drives. And just to show you another example, let me go ahead and show you the one in the book, which has an extra drive. So that one would be this one right here. So this one has 5 drives. So we got block 0 to 3, which is 4 blocks into the first parity bit, which is a little bit weird because the next one has 3, and then the remainder ones have 3. But that's okay. That's just so that you can interleave things properly when you have things that are not perfectly divisible. So here we have 4, 5, and 6, and then we have the parity bits for 4 and 7 here. Why is this for 4 and 7? Oh, I see now. I see. Okay. Yeah. So I think I might have done the math wrong a little bit here. So actually, you still have the same numbers as before. You just move around. Yeah. I apologize for that. Yeah. So actually, let's go ahead and redo that. Okay. So we got blocks 0, 1, 2, then we got 3, 4, 5, and then we got 6, 7, and let's just say 8. Well, let's do one more row. 9, 10, and 11. So if here we would have parity bits 0 to true, 3 to 5, 6 through 8, and then 9 through 11. So this will be RAID 4 technically. This would right now, I would literally be RAID 4. The way we're gonna make it RAID 5 is we're gonna move things around. So we're gonna, for example, for the second row, we're gonna move the B5 here, and actually move the parity data in here, like that. And then for this one, we're gonna take this out and we're gonna move it there. And I guess we'll put it like that. The idea is simple here. We just want to put the parity bit data into all of the drives instead of just having one drive with the parity bits. And this same concept could be applied to pretty much all of the other ones that we did, except for the Hamming code one. We could do this in RAID 3 too as well, but that just makes life really weird. So no, don't do that actually. But yeah, so basically by doing that, you know, because the bottleneck of RAID 4 is the fact that the parity bit drive is everything parity bit, and we always have to access that drive. And in this scenario here, because the parity bit drive, and of course if you're having multiple IOs, you know, and they're all accessing the parity bit drive, then that becomes an issue. Here, because they have the parity bit information distributed amongst the other drives, then that makes life easy to basically, you know, if say we're accessing data related to this, and we're accessing those pieces of data, and then we're accessing the parity bit for that, so that's here. That's cool. So then maybe then later on you're accessing this piece of data, so you're accessing the parity bit for that over here. And so as you can see, there's less bottleneck versus like with RAID 4 where you're always accessing the same data the same drive for every single access, and we don't want that because that is a bottleneck. So in the example they gave here, we got blocks 0 to 3 are here, then we got 4, 5, 6, and 7 is here, we got 8, 9, 10, 11 here. So basically we're taking these, as you can see here, and we're sort of distributing it along so that they're all over the other drives, so that we kind of even out the usage load. So that's pretty much the difference between 4 and 5. The 5 basically distributes the parity bit over the other drives to basically be able to ease the load of it, and it gets you a good aggregate transfer rate. And it does, however, make it difficult to rebuild in the event of a disk failure, but it's possible to do it, because now you got to figure out, because the parity bit's all over the place. You know, I mean, it's painful, but at the same time, you can still use your XOR operations. And you can look at the book where they kind of, fortunately, they don't really talk much about RAID 5. Yeah, they don't. But if you look at the tables, then they do. Turns out that RAID 5 is what they use in data servers, database servers, web servers, most internet stuff. File and application servers are all going to be using RAID 5. If you're watching this on YouTube, which you are, then you're probably getting it through some sort of RAID configuration as well, because it's wherever it's stored on the internet, it is stored in RAID probably. It is the most versatile of the RAID levels, and it's probably the most popular as well. It's used in just about everything. Okay, so that's the one that you really want to know for the real world, I suppose. However, and you need, again, just n+1 drives. And instead of putting all the parity stuff in one place, you distribute it. So that's why things get shifted around. Okay, so that is going to be your RAID 5, and similar to RAID 0 in terms of reading, which is good because that's the one where you distribute stuff out, so you can read things at the same time. You know, if I'm trying to read this row, I can read in from all three at the same time and read it in the time it takes to read one, right? So that's great for reading. It's a little bit lower for writing, you know, but most of the time in things like file and data servers, most of your activities are reading related and not writing related. And if they're writing related, you don't really have that pressure of having to write quickly. In servers, typically, you just want to access. If you go watch on YouTube, the only time that you're it's all reading. You're just reading information from YouTube. You're watching videos. You're reading in the data from the drives. If you're uploading a video to YouTube, then you're writing to it. But it's not in a rush. So if you're writing to it, you don't care too much about if it takes a little bit extra time. And so that's a good trade-off. As long as you have good read rates for servers, it's not too bad to have a little bit slower for write. Okay? So yeah, that's and again, you still got to compute the parity bit and all of that. So finally, it takes us to the final one that is going to be RAID 6. So RAID 6 is known as blocked interleaved dual distributed parity. So this one again is, well, another name for 5. Yes, the book says block level distributed parity, but they also use block interleaved distributed parity. So those are both okay. So RAID 6 is going to be the same thing, but dual. Block interleaved dual distributed parity. Okay, so that one requires n+2. So you're gonna need one extra drive than the other scenarios, ignoring level 0 or Hamming, or sorry, level 1 and level 2, which are the mirror or Hamming code. Data availability is going to be the highest of all alternatives. And for large I/O, it's going to be similar to RAID 0 for read, a little bit lower than RAID 5 for write. What it is again, I'll pull up the picture for that one. It's going to be, you put in basically 2 check bits. Essentially, that's what you're going to do. You're going to put 2 check bits, parity bits, actually. And what you want to do is basically, by having 2 parity bits, you can have up to 2 drives fail and still be okay. So instead of having the risk of 1 drive failing and that's like over, it allows you to have the chance of 2 drives potentially failing. Although you do incur a substantial write penalty because of this if you are trying to run on a system that has 2 drives that failed. Trying to figure out what you want to do for that does kind of incur quite a bit of a write penalty for that. It can suffer about 30% drop as well in general performance, even if you don't have any drives that fail for writing. For reading, they're about comparable between RAIDs 5 and 6 though. And so yeah, that's pretty much it. It basically, if you want to take advantage of RAID, but you don't want to play with fire by saying, okay, if 1 drive fails and it's like, oof, we're kind of iffy here, then you go with the thing. We're like, okay, then there's less chance of 2 drives failing. And so with RAID 6, you have that dual redundancy, which means 2 drives can fail. And again, you do that by having 2 parity bits. Again, you don't want to just have the 2 parity drives. You want to interleave them. Otherwise, imagine RAID 3 with an extra parity drive. That would be even worse for bottlenecking. So what you do is you split it out like this. And by doing so, you maintain the benefit of RAID 5 with no bottlenecking, but you have the advantage of having the ability to recover from 2 disk failures by having 2 independent checksums, okay? And what is it used for? Basically when you want to be extra safe. So like mission critical applications that you really don't want to have the potential risk of this thing dying, then you are like, well, I mean, you still got a risk. If 3 drives fail, then, I mean, you're screwed. But ideally is this. Let's say that a drive fails. What happens in the real world is if a drive fails in the data center, they're not going to shut it down. Everything's going to keep going because you can't build the parity. With the parity, but you can rebuild the drive, right? And you can, if you need information, you can rebuild it on the fly. So let's say that it takes about a day. Well, not 6 hours. Let's say it takes about an hour to fix the drive if it fails. And then maybe it takes another hour to rebuild the drive with the parity information so that it's ready to go. So you would say 2 hours from like the initial downtime to it basically everything is back up. That's the time where if a second drive failed with the other RAID levels, where you would have a problem where you're like, oh shoot, well that's it, I lost the data. It's all gone forever. The whole RAID array is gone. So what you do is you say, okay, in those 2 hours, what are the odds of a second drive failing? And the odds are extremely low. I mean, it's already low that the drive fails in the first place, but it will happen. And if a second drive fails, then you're really just that unlucky. However, if you want to be extra safe and you think that the time to exchange your drive is too long of a time to risk it, then that's when you do the level 6. Because then, if while you're replacing that first drive, a second drive fails, you still haven't lost the data. You will need a third drive to fail. And hopefully by the time that you fix the first drive, that is rebuilt, and then you're going to fix the second drive, then if another drive failed, you'd be okay. As long as you fixed it one by then and rebuilt the data from the parity bits. Or the checksum bits, which is just a different word for the same thing. So essentially, that's going to be your level 6. You have 2 chances of failure before you run into problems by having that extra thing. And that basically just means 1 extra drive, which is a acceptable cost. If you got 100 of these drives, 1 more drive is okay. It's still better than having code. Having code doesn't really gain anything over this system, but you still use a lot more drives. Because again, the only reason for Hamming code instead of just the even or odd is because Hamming code will tell you which drive failed. Whereas this does not, no other one of these methods tell you where the drive failed. You're gonna have to use a different system for that. But that, typically the drive again will be a catastrophic failure where it's just not even gonna spin. And then that way that the problem is. But you do have a performance drop of about 30% by having the second drive. So there is definitely, it's more than just, putting another drive and paying another $50 or whatever for the drive. No, you are going to have some sort of efficiency loss potentially. Okay. So yeah, that is basically RAIDs 0 through 6, and you should definitely at least for sure remember 5. But it's good to know all of them, because if you ever work in a data center, or actually you can set up your own RAID configuration at home. You probably want to do something like RAID. Don't do RAID 0. That's a horrible idea. But do something like RAID 1. Just mirror your devices. That's pretty cool. And for home usage, it's cool. It's nice. There's specific drives that already come, or not drives, kits that come to prepare RAID arrays, and you just buy the drives and plug them into the kit, and it does all of the handling. That is for like people who have no idea what's happening. They just plug in the drives and let the RAID take care of themselves. Or you can do your own thing by actually installing software that manages it as well. There's also something known as nested RAID, in which they put different systems together. Like they'll put RAID 6 and 0 or 5 and 3 and weird things. But we're not really going to talk about that because that's beyond the scope of this. So that basically concludes the discussion on RAID. I hope that you found it interesting as well. So now we're gonna briefly talk about chapter 6 now. So yes, I'm debating if I should just start a new video at this point, but sorry, not chapter 6, chapter 8. Yeah, chapter 8, right? This is chapter 7. So chapter 8, I did assign it for you to just read it, but I did say to kind of go briefly about it. We just don't have the time to talk about in detail. So chapter let's actually open up the PowerPoint for it. We don't need this anymore. Chapter 8. So Chapter 8 is dealing with I/O and how it works, essentially, and the kind of problems that we run into I/O. So first of all, what is I/O? I/O is going to be input-output. It can be anything from a printer, a modem, Ethernet card. A hard drive could potentially be considered as I/O. There's a wide variety of peripherals, essentially, and they all work by delivering different amounts of data at different speeds and different formats. And they're way slower than the CPU and the RAM typically. And it's very inefficient to connect them directly to the system bus because that would be a lot of things to keep in there. And because they're slow, they're going to hop things and whatnot. And the CPU shouldn't really have all the control logic for these peripherals because that is just bad. So you essentially are going to end up needing an I/O module. And here's an example of that I/O module, where communication between the peripheral and the bus has to do with interfacing CPU and memory. And so it gets pretty complicated, actually. But what I really want to get you out of this is that there's three main categories of external devices. And those are human readable, machine readable, and communication in general. Human readable are going to be something like your terminal or even a printer, actually. But by terminal I mean like a printer, like the screen. You know, what you see on the screen is human readable. Machine readable is when you're sending something to like an external hard drive. That would be considered, I suppose, an I/O as well, or external storage of any sort. And finally, communication being whether you're communicating to like the internet, you know, and sending something over the net per se, right? And so between all of these, there's some major functions that you should be aware of, and those are the main categories. We have control and timing, processor communication, device communication, data buffering, and error detection. Error detection we have talked about already today and also before, yet again. With the error detection with the hard drives, you know, with the RAID stuff, but with memory, you know, there can be errors in transmission. You can already imagine that when you're sending something over the internet, you might have like what's known as a package loss and things like that, where you lose data. And you want to make sure that A, you either detect the data so that you can request it again, or B, build it on the fly with something like a parity bit. Data buffering falls into the issues that because there is different levels of speed between the different devices, you may need something to kind of put data in between to be able to send it, so like ready to go to send it. Or you could also have the situation where you receive data, but you can't process it that minute. So you gotta leave it somewhere to kind of be stored while you get to it. There's also with the control and timing. Well, here I think that's enough for that. Let's move on to actually talk about different kinds of programmed I/O. So here, let me pop the book up, and just I want to make sure that while I briefly cover this, I don't miss out on any of the big things that I wanted to say. So it's important to know that there are those three categories of devices, and the different functions. Let's just very briefly touch them actually with these. So I already talked about detection, buffering. I think might as well talk about control and timing. That's on page 250, and there's a list of things that they do. But it basically, control and timing coordinates the flow of traffic between the internal and external. Oh, that's what it literally says here. Resources, and what that really goes and says is the checking of the processor to the I/O module to check the status of a device, and you know, it's like, hey, are you alive? And then the I/O returns a status like saying, yes, I am ready to accept commands or ready to transmit data. And then, if that is the case, then the processor is basically going to tell the I/O device, like, "Hey, okay, please take this information. You know, I am going to request to you. I'm about to send you this very important message that you're supposed to do. Okay?" And then you send it over, and because the I/O device is like ready to receive, and so the I/O, you send it over to the device. You know, over some certain unit of data, 8 bits or 16 bits or whatever. And the I/O device receives that data, okay? And well, first you actually tell it how big the data is going to be and how you're sending it by pieces, because the data flow is just going to be a stream of bits. So you got to tell it like, are these like 32-bit addresses? Are they like 16-bit groups of data? So that it knows, right? Like where one thing begins and ends. You know, otherwise you send like 100 bytes. 100 bits of data, and it's like, what the heck? Is this one big number that you're sending me that's 100 bits long, or is it like 20 different like numbers that are like 4 bits long? Like, what is this, right? So you gotta tell it how you're gonna flow the data. So like, I guess a picture is in hand here. So suppose that you're gonna send it these 2 pieces of data, okay? You gotta tell the I/O device like, hey, I'm gonna send you these 4 bits pieces. That way, what you're really gonna send it is just this. However, you want to make sure that the I/O device interprets this as 2 separate pieces of data, not just one big data, right? So you tell it ahead of time the unit of the data transmission that's going to happen. And you could have this as some hard-coded value, but typically it's optional. It's a thing that you set ahead of time. And finally, you go ahead and send the data, and then you get your hello world printed to the messaging. So there's command decoding and status reporting and a lot of really complicated things going into this. So make sure you kind of go and look over that. So processor communication is going to be that decoding and data status reporting and address recognition. Address recognition is just as basically that just like main memory has an address for each location, so does an I/O device. And so an I/O module must recognize one unique address for each peripheral that it controls. In terms of command decoding, there's things like read sector, write sector, seek, scan, and so on. And status reporting is like when you're telling the I/O device, like, are you ready to receive data? And then it basically reports to you as ready or as busy, because it might be busy doing other things for other, it might be reading an information from the user, or it might be still writing the last command that you sent it. And so there are three main techniques for I/O, and each of these is a section in the chapter. There's programmed I/O, there's interrupt-driven I/O, and there's direct memory access. And so, you see my notes for that. Let's talk about the first one here. 1 second. Here we go. So, programmed I/O occurs under direct and continuous control of the requesting program. And interrupt I/O is basically the program issues an I/O command, as we saw before, and it basically just forgets and lets it be until the interruption for confirmation that it finished. That's the interrupt that we talked about some time ago. And the first one is more of like the one where it just waits for it to actually get things done. And then direct memory addressing is a specialized I/O processor that takes control of the I/O. So you basically have like your secretary per se, and the secretary deals with this. Okay? So the steps to do the programmed I/O, for example, is going to be that the CPU requests an operation, the I/O module performs the operation, and then the I/O module sets a status bit. Then the CPU is going to, and the status bit is going to be like, I'm busy working, or I'm not ready yet. And then the CPU is basically checking the status bit periodically, like, are you done yet? Are you done yet? And it's just checking it. Are we there yet, kind of thing? And it just says that it's like working, right? So the I/O module is not directly informing the CPU what's happening. Okay, the I/O module is just having a status light, like busy. Think of like if you are in an office and there's a little light that is saying that the room is busy, and you're just waiting for that light to turn off. So you, like an airplane, the bathroom of an airplane, you see the light is red, and you are occasionally checking it because you want to go to the bathroom. And what you do is you check it occasionally, and you go do something else, and you come back and you check it again, and you hope that at some point it's going to go green, right? It's possible that it went green for a second, and then somebody else went in and took it, and now it's red again. Like, that could happen, Basically, you as a CPU have the ability to come back to it later if necessary, okay? There's no interrupts because you're essentially sensing the status of the I/O device, okay? So that's what program I/O is going to do. And it's bad because you're wasting CPU time when you're actually sensing the status, right? Because so like, let's say you're in a plane and you're working on your homework assignment for the class, you're coding that IAS computer, and then the time it takes for you to stop typing and look at the bathroom light to see if it's on or off, if it's green or red, is a waste of your time because you're wasting physical time of stopping typing, turning your eyes over, checking the data, checking the light, processing your brain if that's a green or red, unless you're banned and can't see the colors, in which case you have to figure out another way. But yeah, so you have to do that processing of time and then come back and figure that out. Okay, so the CPU can also even be waiting for it. It's just waiting. You could be just looking at the light, waiting for it to like finish. Okay, but you could also be potentially doing something else. But you're the one in control of that. Okay. On the other hand, with interrupt, that is what we know. Where basically the CPU, there's no checking. The CPU doesn't do any checking at all. The CPU is doing it. It's actually working on its own thing. And what happens is more of like the I/O module interrupts you when it's ready or when it's done. So from like a CPU viewpoint of view, if you issue like a read command and you go do something else, then you just simply check for an interrupt at the end of each instruction cycle. And if you're interrupted, then you go ahead and you save your context, you save your registers, and then you process the interrupt by fetching the data and storing it, and then you return your context by getting the data back to the registers. So that is what we talked about when we talked about interrupt. Now, I know you're thinking, checking for the interrupt is kind of like checking for the I/O, but it's different because here's the thing. In the CPU, if you get an interrupt, it's going to be already in the CPU. In the first method with the program I/O, you actually have to go and look at the I/O, which takes time because you got to communicate with the I/O device essentially. That is a lot slower process. It's kind of like thinking the difference between a buzzer coming out when somebody comes out of the bathroom, so you don't even have to look away, you hear it, versus like you having to look into the light of the bathroom, which is a little bit slower. Okay, so that's kind of what interrupt-driven I/O is going to be in comparison to programmed I/O. In terms of the comparison between both of them, you are able to do something else in the meantime with interrupts, and it's faster to be notified if something is done or not. So interrupt I/O is going to be essentially better. But the challenges with that is how do you identify which module issues an interrupt? And if there are multiple devices, okay? And how do you deal with multiple interrupts as well? We talked about sequential or priority based, like interrupt inception, right? So the way you can do that is you could have a different interrupt line for each module that you could do. So each module can create a different interrupt and then you can give them priorities. But this is kind of impractical if you have a large number of devices. You could also have a software pull where each module shares the same interrupt line, but the CPU detects the interrupt and starts polling, asking like, okay, like somebody tapped me on. It's like imagine you're working on this and you hear a buzzer, but you don't know who called you. So you start asking the I/O devices, yo, who called me? Who interrupted me? Like, who is it? Like, was it you, printer? Was it you, terminal, like screen? Was it you, internet? Who was it? So you poll them by asking them and figure out who it is. This is of course really slow because then the I/O has to actually respond and be like, no, it wasn't me. No, it wasn't me. Yeah, it was me. Okay, let's go. So the software poll is not very efficient. There's also a hardware poll which is a little bit faster that you can do. So that's another method, by the way. And finally, there's also bus arbitration, in which a module claims the bus before it can raise an interrupt. And because of that, it already knows which interrupt is going to be. So those are basically the four sort of techniques to figure out which interrupt it is. Essentially, it boils down to having multiple lines where each interrupt has a priority, but they all have lines. Or they all share the same line, and then you use software polling by asking which one it is. Or you go ahead and do something like daisy chains or order chaining, and there's also bus arbitration as well. So, and they're centralized and distributed within that as well. So, that's pretty much the three different types of programmed I/Os. I/O commands, yeah, sure. There's test, read, and write. Test being for checking things out, like testing the condition if something is ready or not. Control is telling the I/O device to do something or be ready to go. Read is for reading information, write is for that. Oh, here, this is perfect. This picture is good, actually, for the comparison between the different, between programmed I/O and interrupt-driven I/O. Yeah. So here you can see issue read command and I/O module, and then here in the interrupt base, it can do something else, and then eventually it gets the interrupt, and then it does things, whereas here, it's actually reading the status of the I/O module repeatedly, and so on. So, yeah, you can see here that it's constantly checking. So, yep. Then you talk about how to store information in the I/O device. Oh, I didn't talk about the third method, the direct memory access. So, the direct memory access. So here's the thing. First of all, let me tell you the reason why. Interrupt-driven I/O is better than program I/O because the interrupts are just better. The CPU doesn't have to waste time, but still require an active CPU intervention, right? Because you still have in the instruction cycle that checking for the interrupt, right? And also, the CPU can get tied up with this. So direct memory access is a solution to this problem because it moves data between system memory and a peripheral without bothering the CPU, and is especially good for large data transfers. So essentially, when you're writing, and this is kind of what you're doing in the IAS emulation thing, you're just saying write to a specific address, and that address you can assume it can be an address in main memory or an address in the I/O device, and it doesn't matter because either way, it gets sent to memory first, and then memory is the one that handles the I/O device. That way, the CPU doesn't get involved, and it's a lot faster to do that because at the end of the day, if you're writing something, it probably came from main memory. You know, you load something from main memory and then you send it to your I/O device, right? Well, why not cut the middleman essentially and send it directly from main memory to the I/O device, and then you don't have to deal with the CPU in there, which slows things down. So that's going to be what they know as memory mapped I/O essentially. Okay. And there's also isolated I/O in which they have special addresses that are for the I/O device. So yes, that's the other side of the coin. That's pretty useful to know. Is there a picture of all three techniques compared? Not really, but oh no, actually, yeah, no, here, yeah, direct memory access is here. So it issues the read block command or the write block command or whatever, and it goes to something else, and then eventually it's the memory is the one that's going to be like, yeah, well, this is done. So it allows the CPU to not have to be bothered unless necessary per se. There's two DMA modes, cycle stealing and burst mode, but that we won't really talk about in detail. There's also direct cache access because the DMA is not able to scale to meet the demands and things like that. So you can put a cache for the I/O devices, and you can put a cache for the DMA system as well. An example of that is the internet actually. Like Wi-Fi handles 3.2 gigabits per second. Or 6.76 gigabytes per second. And this is a lot of information coming in and out of a network, right? So like if you're downloading something from the internet and it's coming in super fast to your computer might not be ready to process that information from the internet. So you could slow down the internet, but the information is just coming in. If you miss it, it's gone. So you put a cache in there to basically hold the data while you process it. So you typically have caches dealing with I/O devices as well. And that's pretty much what the rest of the chapter really talks about. There's daisy chain. So, yep. Oh, then they talk about like USB. That might be actually interesting to kind of bring up very briefly. By the way, in terms of evolution, first we had program I/O, then interrupt-driven I/O came out, then DMA came out, and then the I/O modules became had their own little processors and embedded systems, and then eventually the IMO got its own memory as well, which we call the I/O processor and I/O channel and I/O memory. So yeah, so basically the way this thing grew out was first we had in the old computers we had an I/O module, and the CPU would wait for things to be done. Right, there was no interrupts or anything like that. That was program I/O. Then people came up with the idea of interrupts. Then they came up with DMAs. Then the I/O module had its own processor to handle things, which was handled via the main memory. And then eventually the I/O got its own main memory and its own processor, and that's what typically is done nowadays. So that's kind of the evolution of things. But anyways, USB is it's a commonly used high-speed I/O because, as you can see, there's different versions of USB, increasing data transfer rates as we went up. USB 3.1 being, I think there might be 3.2 nowadays, but the reality is that must be just a marketing thing because I think 3.1 is really the fast one. Those the 3, by the way, you usually recognize that because it has a blue color to the plug versus the other ones which are like just gray or whatever. That's how you know it's 3.0. 3.1 is just a little modification of that, but it's one of the most popular I/O devices used, unless you're a Mac person, in which case they have weird things like Thunderbolt and yeah, there's USB-C now too, which are variations of USB for different sizes and things like that. So yeah, I think that's all I want to say about the chapter. Again, we're just kind of going very briefly through that. So you're aware of I/O, but really we don't have time to kind of go too much into detail for it. So hopefully this gave you sort of a quick and brief overview of chapter 8. Again, do read it. you know, get more information on it. There will be some questions on it on the test, but it'll be very light per se. Okay, so that's pretty much it for the day, and I hope you guys have a wonderful day. Thanks for watching. Take care.